I will start off here where I had left off in my last lecture, and there I had described the semiconductor laser, not the laser, just the semiconductor structure in terms of the energy band structure, the energy levels that are occupied by electrons and holes. And we had also seen there that the electrons and holes in this kind of a theory is treated as different particles. You know, the hole is also a particle, just like an electron is a particle. They are called carriers in the language of the semiconductor physicist. So, I had left off there. So, after that now today I go ahead immediately after that, and let me see how it goes. So, I start off with here with the absorption and the emission process in semiconductors. So, as you can see this band structure, I have drawn it again here, this band structure I have drawn it again. So, in case of, and what you can see is in the valence band there are a few holes and there are a few electrons too. In the conduction band also there are some electrons, some holes. So, it is sort of a mixed state at this moment. So, now if this electron were to be absorbed, so there is an input photon and this will be absorbed and it will go up to this state here, which is a hole. So, it is called electron hole recombination, and it will not happen unless a hole exists in the conduction band and unless an electron exists in the valence band. Okay. So, this is the absorption process here, and you can also see that the photon should have an energy which is larger than this at this point. This is the band gap. Okay. You have to overcome the band gap. The photon should have a frequency such that this energy difference is crossed over. Okay. So, this is the absorption process. Now, I will have a emission process. Now, the emission process is you will catch hold of a electron in the conduction band, and if it drops down to the hole, recombines with the hole in the valence band, then there will be a photon which is emitted, and that will be equal in energy to this difference in energy. Okay. And again that is more than the band gap here. So, the band gap is for the the lowest most of the electron conduction band and the highest most of the valence band. So, this is the emission process, and this emission process is called spontaneous emission, the one in the blue line, because it has happened on its own. Nobody has triggered anything, nothing else has triggered it. So, it just happened, and so it is called spontaneous, and it will be in any direction. It does not have any particular direction in which it is emitted, and this forms the basis of LEDs, light emitting diodes. Okay. But then there is another emission process which is called the stimulated emission process. And you are already familiar with it because I have described stimulated and spontaneous emission for the other kinds of lasers. It is nothing different here, only the energy band structure and the energy level structure is a bit different. So, I have a photon which is impinging on this semiconductor, and it nudges this electron to fall down to this hole which exists here. Okay. So, this process is a stimulated emission process, and the photon that is emitted has the same direction as the input photon, has the same coherence as the input photon. Okay. And so directionality and coherence is the same as the input photon. And this is what forms the basis of the lasing action in semiconductors. Okay. So I have lasing action which is taking place here, stimulated emission, not lasing exactly as yet, stimulated emission process, which will finally give rise to the lasing action or amplification of light. And then I have the spontaneous emission process, okay. And I have the absorption process also. So I have these three competing processes, and I have to somehow ensure that this stimulated emission rate is higher than the other two. Then only I can get light amplification, all right. So, in order to do that, we must know, we must have a larger number of electrons here in the conduction band and more number of holes in the valence band. Then only this sort of process will take place. But how do I go about finding the number of electrons? So, before that I must know the number of states that exist in the conduction band. I must know the states that exist in the valence band, okay. And after that, the probability that the electron or the hole will be occupying those states. So, first let us talk about the density of states that are available to us, okay. So, in case of the density of states, if you just recollect the formula for this E, it is here, it is right here, just concentrate on this. So, if you can see this k values are k, the wave vector for the electron, they are equally spaced, okay. The k values are equally spaced, but the E values goes by k square. So, they are not equally spaced. So, we really must know the density of states, okay. That means the density energy levels within a small part of the energy of E and E plus dE, okay, energy states per unit volume. That is our final aim. That will be the total number of density of states. So, in order to start off, we start off with the number of allowed k states itself, and E is anyways dependent on k, okay, it is proportional to k. So, in 3 dimensions, the number of allowed k states within a spherical shell of radius k and thickness dk is proportional to the volume of the shell in k space. So, we are just concentrating on the k space before we go on to the energy space. So, in the k space, we must find the density of k, okay, or the total volume of this k. So, let us concentrate on this volume. So, what I am talking about, this spherical shell of radius k and thickness dk, just imagine it like this. This is one sphere, okay, and then there is one more sphere here, and we are talking about the volume between these two spheres, okay. So, k is the radius, and this part, this small little strip kind of a part, this part is dk. So, we want to find the total number of states within this small strip here. Okay, within this small volume which is here. Okay. And how can we do that? That is described as Pk dk. Okay. Pk is Pk and dk. What should it be? So, I am in the k space. this is with a radius k. So, I should take the surface area of this this sphere and then multiply by dk, okay, which will give me the volume, and surface of a sphere is 4 pi k square, 4 pi k square, and if I multiply by dk, it will give me this volume in this small bit of thin sphere. Okay. So, pk dk, the probability of k being between k and dk, that is pk dk, will be proportional to this volume, and also remember it will be proportional to k itself, you know, and remember k is given by 2 pi by L. So, it will be proportional to the volume of that k. So, if you can remember, the electron is confined to a volume of length L into L into L, that means it is confined in a volume of the cube. Okay. So, that is given by L cube. So, pk dk will be proportional to that the volume of that thin bit of spherical range and also this volume. So, that is how this term comes about, L cube by 2 pi. Okay. So, so my probability of finding k between k and dk is this formula here. Now, I go to the density of states, because that is our final aim. Density of states lying between energy E and E plus dE is given by P dash E dE, which is equal to pk dk. Okay. It will be equal to this, because each of them are mapped onto, each energy is mapped onto k, okay, by this formula. Okay. So, we will come back here. So, P dash E is the density of states lying between energy E and E plus dE. Just do a little bit of jugglery there and you finally come to, jugglery means just multiplication on either side of the equation, okay, and then you come to this formula. So, P dash E is equal to pk dE by dk and inverse of that. Oh, that is very easy to derive. So, we have to derive dE by dk, okay. We have to derive this. So, we do it from this equation, this is already there. So, you take the k square onto one side of the equal sign and you put the energies on the same side of the equal sign, and here you have the derivation, you take the derivative dE by dk, just do that bit of derivation and jugglery here on either side of the equal to sign, and you get mc upon k h cross square. Oh, that should be actually h cross. Yeah. So, h cross square. Now, you just put in the values of pk and dE by dk in the equation for P dash E. So, you found dE by dk inverse, this is that, and you already know what is pk is. So, you put it here, put it in this formula. That means, you are taking pk from here, you are putting it here, and dE by dk from here, you are putting it in this equation. So, once you put it in, you will find that you come to this conclusion. So, you have a value for P dash E, which is the density of states lying between the energies E and E plus dE. So, but then the actual density of states per unit volume, that is what we are looking for. We described k in terms of within a certain volume. You have just got to divide by that volume factor. That means, I have just divided by L cube here, and I get this is my final density of states per unit volume. And you can see it is proportional to E minus EC, the root of that. EC, as you can, if you recollect, was this part, this energy level here, just at the bottom of the conduction band. Therefore, C stands for the conduction band. Okay. Then what do we do with this? So, this is the density of states for the electrons I derived, and you can do the same thing for the holes, exactly the same thing. Here I just write down the density of states, energies lying between E and E plus dE for the conduction band and also for the valence band. The green one is for the conduction band, and the one in brownish red is for the valence band. So, see, I have put this factor C here, which shows the conduction band, and I have put this factor V here to show this is for the valency band. Okay. So, these are the density of states in the valence band. This is the density of states in the conduction band. And as you know, for the density E is always less than EV, because all the states come below the valence band. This is EV, just to recollect again, this part is EV. So, all the states here, they are all below here, and in case of the conduction band, they are all here above EC. Okay. So, that's the that's why you get, you know, this sort of a formula, EV minus E, while here it is E minus EC, and okay, the root of that. So, here I have got the density of states in the valence band and in the conduction band. Now, to know the density of electrons that are occupying above the energy states, the probability that the state of energy E is occupied by an electron is given by the Fermi-Dirac function. Just getting the density of states is not enough. You have to know whether the electrons are occupying that state also or not. And okay, we have the Fermi-Dirac formula, which gives you the probability of occupancy. So, this is the Fermi-Dirac formula. It gives you the probability of occupancy of those states which exist, okay, in the conduction band. Remember, last time in the last lecture I had just put in this formula, I had not put in the value of mu. Mu is actually a special state called EF. This is the Fermi energy level state. This is a Fermi energy level. Okay. And so, the actual formula for the probability of occupancy of the electron in the conduction band is given by this formula, and I have just introduced EF here. What is the significance of EF? Why do I need to put in a term like EF here? If you put in the energy, if your energy, some energy state is equal to EF, then this probability turns out to be half. Just put in that, this becomes 0, and so this probability is half. So, I get this F, the probability of occupancy of this energy level E as half. So, what does it signify? Actually, the Fermi level is kind of like a reference level which gives you an idea of the electron occupancy either in the valency band or in the conduction band. So, it is kind of a reference point. I will give you some of the properties of EF just after this, because it is a very important level, and it gives you an idea of the electron hole distribution in the two bands. But before that I think I should talk about the momentum conservation. Okay. absorption and emission should also satisfy another condition on the wave vector k of the electron before and after transition and the propagation vector of the photon. Okay. This is called the conservation of momentum in the interaction process. Okay. So, we have talked about the conservation of energy. Here, when I was describing the absorption and the emission process, there is conservation of energy, because your photon has to have exactly this difference in energy. The photons here have exactly this difference in energy. So, in a sense we have been talking about the conservation of energy, but that is not enough. We should talk about the conservation of momentum too. Okay. So, in case of the electron, K1 and K2 corresponds to K of the electron in the valence band, and the conduction band it is and the conduction valence band and the conduction band. K1 is for electron in the valence band, K2 is for in the conduction band. Okay. It is describing the K of the electron. Okay. But then now there is a new K which is the photon, the K for the photon which is emitted is the propagation vector of the optical radiation interacting with the semiconductor. Okay. So, for conservation of momentum we should have K1 minus K2 is equal to KOP. Okay. So, in this whole process of absorption and emission, or in this whole process that the electron is going through. So, H cross K gives you the exact momentum minus H cross K2 is equal to H cross KOP. KOP, if you just put in the values of K and H, it comes, in case of this it is H nu by C. Okay. So, that is the value of this. But then intuitively you know the momentum of an electron will be much more than a photon. So, you can sort of neglect this, or you can make this 0, this momentum of the photon should be almost equal to 0. Even if you think of interatomic space, suppose I call it A, interatomic space, then that momentum is proportional to, for an electron, momentum is proportional to 2 pi by A. Okay. In case of the electron, this is the thing. In case of the photon, it will be dependent on the lambda, the K part. Okay, it will be proportionate to lambda. So, it will be 2 pi by lambda. Okay. So, obviously, A is much less than lambda. So, the momentum of the electron is much more than that of the photon. So, that is how I forget about this part, make it 0. The moment you make it 0, H cross K1 is equal to H cross K2. So, K1 equal to K2. What does it mean? This is called the K selection rule. Okay. And it is quite important because the meaning is that whenever there is a transition, when the electrons drops down from here to here, or is nudged to drop down from here to here, or the photon is absorbed by the electron and goes from here to here, all of them have the same K. You see, this process will take place, it is all in a straight line. In this diagram you can see it is in a straight line. Okay. So, the K value of this electron, when it falls down into the hole, it should come down, it should have the same K value. See, it is in a straight line, so it has the same K value. In case of spontaneous emission also, this electron is falling down here. So, it has the same K value, this K value and this K value is the same. Okay. So, and similarly here. So, they are all in straight lines. You can never have an electron coming from here to here. You can never have an electron coming from here to here. Okay, that will not happen. That is the significance of the K selection rule. Okay. It makes life much easier if we have this K selection rule. Okay. So, that is how it is. Now, I can go back to the significance of the Fermi level, all right. I have just listed down here Fermi level, and there is something called the Quasi-Fermi level. So, let me see what they are. The Fermi level divides the range of possible energy states. States below the Fermi level have higher possibility of being occupied. Okay. And the position of the Fermi level determines how likely it is for electrons to be found in the conduction band or the valence band. Okay. And the position of the Fermi level changes based on the doping. In intrinsic semiconductors, the Fermi level is near the energy gap between the conduction and the valence band. In N-type semiconductors, Fermi level shifts closer to the conduction band. In P-type semiconductor, the Fermi level shifts closer to the valence band. Okay, so I should show here position of the Fermi level changes based on the doping. Intrinsic semiconductors, the Fermi level is near the energy gap, between the conduction and the valence band. So, it means like this. This is my conduction band, this is my valence band, and this is the Fermi level. Okay. This is my Fermi level. It is exactly between, exactly in the center of that energy gap, okay, in case of intrinsic. Now, what happens in case of N-type and P-type? Okay. There is a shift in this energy level. So, the Fermi level basically divides the range of possible energy states. So, if I have it here, it divides, and you know that significance of Fe equal to half, this is the probability of occupation of the electron is half at a energy state E. But you can also interpret it as this, that suppose it is in the center of this energy gap. You know, no electron can reside here and there are no energy levels here in this gap. So, obviously, it means that the number of electrons which are above and which are below here in the valency band are almost equal. Okay. So, this is how the Fermi level acts as a reference point, you know, in different conditions of the semiconductor. I will go ahead with this in my next lecture.